Welcome back, everyone, to the final session of presentations from fellows. For those of you who don't know me, my name is Jay Bardhan. I lead computing, analytics, and modeling at EMSL, the Environmental Molecular Sciences Lab at PNNL. And I will be introducing the speakers this afternoon and moderating questions from all of you. Our first speaker today is Louis Jenkins at the University of Rochester. He's in the computer science department, advised by Sripathi Pai, and we would like to welcome Louis up to give his presentation.
Hello, everyone. My name is Louis Jenkins, and my research is on dynamic resource scheduling of Jupyter notebooks at Cell-Granularity. To begin with a simple disclaimer, I'd like to state that my research topic has dramatically changed since early 2022. Originally, I incorporated a lot of persistent memory into my research, but that has been killed off by Intel in mid-2022. But to get into things, what is a Jupyter notebook? It essentially is a web app that enables the creation and sharing of code, equations, visualizations, and it's used in many different domains such as data science, computational science, machine learning, etc. And it runs on many different types of hardware such as laptops, desktops, cloud computing like Google Colab, and supercomputers such as at NERSC. So Jupyter notebooks are composed of blocks of code called cells. These cells can be created and modified and deleted at any given time. They can be run any number of times in any arbitrary order. Cells must be run serially, so you cannot have them run in parallel at the same time. And they can be followed by arbitrary periods of idleness that I refer to as think time. So for example, someone taking a break, someone writing code, someone analyzing results. And the cell's resource requirements can vary wildly. So it also brings up some interesting questions as to how to effectively use them on supercomputers. So for example, job allocations in supercomputers typically are exclusive by nature. So what happens if a notebook has a lot of think time? If it's highly interactive and has very small bursts of computation? Supercomputers also have static and coarse-grained batch allocation schemes. So what happens when you have a long-running cell that's, say, running on a single core? What happens to the cores that aren't being in use? What happens if it allocated a GPU with it and it's not using that for a long time? Supercomputers often have long queue times for allocation. So if you want to go with the route of, say, having each cell be its own batch allocation, then what happens if a data scientist just wants to quickly generate the results for some analysis? What's the acceptable level of responsiveness for an interactive application? So the proposed solution is relatively simple. So we co-locate Jupyter notebooks. So Jupyter notebooks essentially share an overlapping set of resources, which can help offset under-provisioning. Resources get located at the beginning of notebook cells and are only provided resources that they particularly need, no more and no less. I designed a specialized scheduler called the dynamic scheduler, which is optimized for notebooks with think time. To evaluate the scheduler, we utilize two metrics. One is averaged normalized turnaround time, ANTT, which is a smaller is better number. It basically is used to determine the performance of each individual notebook in the system. Then you have system throughput, which is a higher is better number, where it is used to evaluate the performance of the entire system. So I compared the dynamic scheduler to two different schedulers, one in which I dubbed the naive scheduler, which is equivalent to just running multiple Jupyter notebooks at the same time, then letting the operating system handle its own multiprocessing. And second is partitions scheduler, also called the static scheduler, which is a simplistic approach of modeling batch processing by just evenly partitioning the resources to each notebook and then letting the operating system handle that. The dynamic scheduler, on the other hand, makes decisions at the boundaries of each notebook cell. So it determines number of CPUs, GPUs, amount of memory, all via offline traces. And it allocates resources at the beginning of a cell and deallocates it at the end. So for a custom scheduler built around Jupyter notebooks, we'll have to handle 3 different cases. The worst case scenario is when you have no idle time. So that's a non-interactive application. So for example, it's when you have a notebook already pre-written and you're running it from top to bottom. Average case, where you have sporadic but realistic injection of idleness, which makes it semi-interactive, which is intended to replicate a notebook that has a semi-attentive, active user. And then you have the best case scenario, where you have an exaggerated idle time, such as when someone takes a break for 6 hours and they leave the notebook running, or I also call it, oops, I left my notebook running overnight case. And the goal is to find target applications for each of these cases. So worst case scenario, the worst case target application comes down to it is just 4 machine learning notebooks, 2 of which are high compute, notebook A and C. Then you have 2 low compute, which is notebooks B and D. Low compute and high compute basically means number of cores they need. High compute typically uses all the cores, and low compute typically uses a single core. The combination of notebooks will run at least n times. So for combinations, as in like A, B, C, D, A, B, A, C, etc. And if n equals 3, for example, it's possible for A to be ran like 12 times, for D runs about 3 times. The goal is to explore how the schedulers handle these various workloads. As a side note as well, the notebooks are also ordered by how long they take to run. So of all the notebooks, these are the 4 of the shortest running notebooks that are there. And to run all combinations across all 3 schedulers takes about a week of time. So a quick analysis of the experiment, ANTT. So we can see that in the cases where the dynamic notebook shows some improvement, that typically are the high compute notebooks. And basically, this can be summarized as avoiding oversubscription. In the cases where you don't have improvement, such as in D and B, which are the lower compute notebooks, we can see that that's due to the scheduler overhead in of itself. But we can also see the fact that when all of them are run together, A, C, D, B, the benefit of oversubscription avoidance is greater than the cost of the scheduler is less than the benefit from oversubscription avoidance. So in the case of STP, where higher is better, we see the fact that in a similar case, for the high compute notebooks, they perform really well. And in the case of where the dynamic schedule doesn't do as well, it is also due to low compute. The takeaway can be the fact that in the worst case, dynamic scheduler has some benefit of oversubscription avoidance. High compute notebooks tend to show some type of improvement, but it has a high degree of overhead, as is visible when it is running in an undersubscribed system. Naive scheduler has the benefit of handling undersubscription, and of course has no overhead since the OS is handling everything. The static scheduler is mostly in between both, since it has no dynamic oversubscription avoidance and has no handling of undersubscription. Now next is the average case. So in the average case, we have Arcuda, which is a HPC class pseudo replacement for NumPy and Pandas. Essentially, it comes down to it is you change out NumPy and Pandas imports for Arcuda, and Arcuda has a chapel backend, which can be run over multiple different compute nodes, and the front end acts as like a, so essentially it's a client-server infrastructure. I see it as like a poster child here because it can be ran from a Jupyter notebook, and also the fact that it's the most important part is that it has real active users. So Arcuda is a type of application where you can have traces. These traces which contain the list of operations which allow you to recreate the execution while also including information such as idle time, which is the most important metric. So I have a trace. I have traces obtained from actual real users, which contain order operations. And yeah, it says order operations, the operands, time taken, memory consumed, and most importantly, the idle time. I have enough for 4 different compute clusters, which contains 130 million rows, whereupon 1.5% of them have some measure of think time, which has like a mean think time of about 15 seconds. So the future goal would have been to essentially explore the worst case scenarios, which I have, explore the average case, wherein I would basically use the idle time from the Arcuda obtained traces to inject the idle time into existing applications to test that. And finally, in the best case, would have been to inject arbitrarily long periods of time to simulate some people actually taking a break while computing. Yeah. So, and that's all.